All right, everyone. So we can go ahead and get started for today. Just a couple of administrative things before we begin. Um, First of all, I hope everybody's been through all of these links that I have on Blackboard. Uh, Most importantly, what I want to point out is this last link for questions or discussion, anything that's not clear to you, or any doubts or questions you have about the homework or lectures. Please do go ahead and post. I see the only two posts by me here. And from time to time, I will also post hints on this forum. So the idea really is that this is a discussion forum. If you have any doubt, you can be sure that probably half the rest of the class also has the same exact question. So rather than emailing me or Dr. Liu, you can simply post it here. Both of us check this quite frequently throughout the day, and you're likely to get an answer from us within a couple of hours, or actually somebody else who feel free to answer each other's questions also. So how many of you actually had a chance to look at this hint that I posted? Very few, huh? Okay. So that goes to show that yes, you should go in and take a look at this discussion forum. I believe if you have a Blackboard Learn app on your phone, then it sends you updates automatically if anything is updated on the website, or if somebody posts a question or a response to your question and so on. So that might come in handy. The other thing, hopefully you've all seen, is I'm posting lecture videos as well. So lecture videos are just so that you get a chance to go back and revisit what we talked about in the class, especially on some of the things that are prerequisites from your previous courses. I'm going to go relatively fast through those. So if something is not clear to you, or even in the future, make sure you go back and visit the lecture videos. How many of you have taken a look at the lecture videos yet? Almost nobody. Okay, means everything is clear, right? Okay, and lastly, there is this program at Purdue called Impact. How many of you know about this program? Some of you do. Okay, so this is a program where your instructors, professors, go through a semester-long kind of a course to try to redesign the way that they teach. So last semester in fall 2015, I went through this to try to make some changes, try to design this course better so that your learning gets improved. And what I hear is that the people from Impact would be sending you some sort of a pre-survey, and looks like some of you, or hopefully all of you, have got that pre-survey. So please do respond to that. Um, I think just to give you some more incentive to do that, what I'll do is, for those of you who do respond to it, you'll get an extra point among the in-class assignments. You remember from the grading scheme that I had for in-class participation, and from your in-class assignments that I collected last time, you get a point each time you complete that. So completing this pre-survey would give you a point towards that. And I understand that they'll send out another survey towards the end of the semester. Right now, we've just had barely 3 lectures, so it's kind of difficult probably to answer some of those questions. Uh, uh, but please do go ahead and take that survey. And towards the end, we'll also have another closeout survey. Go ahead.
Do you need us to print out confirmation, or do you get a list of all the keys you take?
I'll let you know. I think I can email them and find out who all answered the questions. Of course, they're not going to tell me what you answered, but I'll at least know who answered and who did. But if they can't give me that, then yes, I'll ask you for a confirmation printout or something. Okay. All right. So that's pretty much the administrative stuff. Let me jump back into the lecture. So very quickly, to set things of where we are. We've basically done some introduction on what really is the problem statement for structural analysis. Once again, what we are really doing is trying to find how structures in general respond to loads. What we are given to be able to try to solve them is the geometry of the structure, material properties, deformation properties, and boundary conditions. So we are using these four concepts: equilibrium, compatibility, boundary conditions, and material properties to try to solve how structures behave, right? So we've last time we had started doing some basic calculations on how to find deflections of beam type structures. So again, in this course, we are primarily going to restrict ourselves to trusses, beams, frames, and a little bit of composite structures. So for beams, we saw quick ways of trying to get approximate deflected shapes just by doing bending moment and shear force diagrams, right? So this is also the exercise that we did last time. And last lecture, I believe we were just about here on this method of double integration. So I pointed out last time that the real equation that we are solving in structural analysis is this equation. This is nothing but the definition of curvature or the bending. This is a flexure equation. M over EI is equal to d square y over dx square. And this is clearly a second order differential equation. And the way we solve differential equations is by integrating them. And we saw last time that if you integrate this equation once, we get dy dx is equal to whatever that integral turns out to be plus a constant. And if you integrate it again, then you get the deflections. So this guy dy dx is really the slope at each and every point along the beam, and y is the deflection along the point of the beam. But as I pointed out last time, this creates these two constants, C1 and C2. So for every section of the beam where you have these two constants, we find those constants using boundary conditions or continuity conditions, which we'll take a look at through an example right now. So this was one of the examples that we had also looked at previously. In this case, we clearly have these three segments, and we've already done the shear force and the bending moment diagram and the rough approximate deflected shape. Let's see now if we can actually find precisely what that deflected shape would be. Okay. So in this case, we have these three segments, one from the fixed point to the internal hinge, from the internal hinge to the center of the support where the moment diagram has a different equation, and the third part here. So anytime we have these different segments of a structure, you have to repeatedly apply this logic of integrating twice to each segment independently. So for example, in this case, you have three segments, and if you integrate twice each of those three segments, how many constants are you going to get? Two for each segment. So 3 times 2, a total of 6 constants. 6 constants of integration, which means you need 6 boundary conditions or 6 continuity conditions to be able to solve for all of those 6 constants. And let's see what those boundary conditions are. So clearly at the left end, there are 2 boundary conditions. Can anybody tell me what those are? Go ahead, say that. Deflection and slope are both 0, so we'll write that out here. Indeed, one is that slope dy dx at x equal to 0 is 0, and 2, y at x equal to 0 is 0. How about at this point 3? What should be the continuity condition? Deflection continuity means, of course, deflection from the left side and the right side should be equal. So indeed, y at x equals a minus, which denotes the left-hand side, is equal to y at x equal to a plus from the right-hand side. That's, of course, just saying that The slope is not continuous, but the deflection itself should be continuous at 3, right? How about 4 and 5 here? What are the continuity conditions at this point in the beam, at the center of this second span? Slope and deflections are equal. Why do we even need this condition? I mean, if the beam is pretty much continuous from here all the way out to here, so why can't I use this entire thing as one segment? Any ideas? Go ahead. That's right. So the loading P here makes the moment diagram, bending moment diagram, discontinuous. Well, it's continuous, but the slope of the moment diagram is discontinuous. So the equation in this half is different than the equation for M over EI in the other half. So that's why we need some condition of continuity here. And indeed, those continuity conditions 4 and 5 are just that y from x equal to 2a minus is equal to y from x equal to 2a plus. From the left and the right, displacements have to be the same, and dy dx at x equal to 2a minus is equal to dy dx x equal to 2a plus. Slope and displacements both have to be equal. And finally, as you can probably see, that the last condition is simply that y displacement at 3a has to be equal to 0. Those are the 6 boundary and continuity conditions that we will need to solve for all of those 6 constants of integration that I'll show you in a minute where they come from. Any questions on this? Any of these conditions? No? Okay. So continuing with that example, I'll just show you the initial steps of this, and I'm sure all of you know integration very well, so you'll be able to apply the same logic to the other segments. So just let's take a look at the first segment right here. In this segment, I know that the bending moment diagram from the previous page, in this segment, the bending moment diagram goes from here all the way to 0. What is the equation for this bending moment diagram? From here to here, it's P minus P over 2 times A plus P over 2 times X. Okay. The value that we start at is minus P over 2 times A. The slope here, since it goes all the way up to positive P over 2 over a length of 2A, is simply P over 2 times X minus A, and that's what I have here. This is the equation. It's a linear equation for the bending moment, right? I can easily integrate that just by writing M over EI as P over 2 EI X minus A. Integrate that once, and we get P over 2 EI outside X squared over 2 minus AX, and what? Anything else? The constant that we will need to find. So plus C1. I'll integrate that once again. I'll get P over 2 EI X cube over 6 minus AX square over 2 plus C1, sorry, I'll write that in red, plus C1 X plus C2, another constant, right? Now, the most straightforward way to find these constants is to just apply those conditions that we had derived on the previous page. We know that the slope and the displacement at left end has to be 0. Applying this first condition, dy dx equal to 0 to this first row, what do we get? That dy dx at x equal to 0 has to be 0. So if I put in x equal to 0 here, I get this. This is 0, this is 0, which means that C1 has to be 0, right? So clearly C1 has to be 0 because of condition 1, and which means that this C1 is also 0. And through the second equation, y at 0 equal to 0. So this goes to 0, this goes to 0, this is already 0. So that also implies that C2 is 0. The second condition implies that C2 is 0. And I'm not going to go through the rest of these steps. I think they are pretty self-evident. But essentially, what we did here was in the first quadrant or first third of this structure, 0 to A, we integrated it twice, applied the boundary conditions, and found the constants. If you keep doing that for the other two segments also, you'll see that you'll create 4 new constants: C3, C4, C5, C6. And you have 4 other boundary conditions to be able to solve for them. So essentially what that means is that you have 4 equations and 4 unknowns, and you should be able to solve for all of them, right? And without going through the algebra, I've given you the solution. Make sure you go through that. If anything is not clear to you, again, post to that discussion forum I was telling you about. Okay. Any questions on this method? Pretty straightforward method, but it's pretty much the one of the only methods that gives you an actual equation of deflection and slope all along the length of the beam. If you try to remember from your previous courses, all the other methods, moment area method or conjugate beam method, if you've learned that, slope deflection, moment distribution, any method that you pick, you get displacements and rotations at specific points along the structure, right? You don't get a continuous equation like theta as a function of x or y as a function of x. This method really is the one that gives you that, because it's actually solving the underlying differential equation. Make sense? Okay. All right. So let me go on to a quick review of the moment area method. So for simple structures, it works pretty well. Now, you might ask, first of all, well, if we already have the double integration method, why do we need all these other methods at all? And the straightforward answer to that is that quite a lot of times you'll have structures that have continuous, too many segments, lots and lots of segments. So if there are lots and lots of segments, twice that would be the number of constants you will have, unknown constants. And you'll need to integrate, you'll need to solve a big system of equations to be able to solve for all the unknown constants. So moment area method is, of course, a semi-graphical method, which allows you to find critical values of deflections and rotations at specific points. And it basically rests upon these two theorems. Theorem 1, which hopefully you all can see that it's really just a single integration from the double integration method that I just talked about. Theorem 1 is pretty much nothing but the single integration. And the idea really is that we are integrating the definition of curvature. Kappa, if you remember, maybe I'll write that here. This really is curvature, kappa. And what does 3 equal to signs means? Defined as, yes. So whenever I write 2 equal to signs, of course, that's the regular equal to. But when I have these 3 equal to signs, it means that curvature is defined as d theta over dx. What is theta? Theta is the slope along the length of the beam. So if this is my beam, under some deflected, under any type of load, you can see that the center line will make some angle with the horizontal. That angle is theta. Okay, and I think I'll add it here. So curvature is defined as d theta over dx. When shear deformations are negligible, then it happens to be equal to d square y over dx square, which is nothing but m over ei. So these are all equivalent uses of curvature. Curvature is kappa or d theta over dx or d square y dx or m over ei. They are all referring to the same thing. And essentially it is referring to the rate of change of that angle along x direction. Okay, and clearly if you integrate that once, you get theta. So for example, in this case, if you integrate the moment or the curvature diagram, M over EI diagram, between 2 points A and B, then the change in the angle between those 2 points is simply theta at B minus theta at A is equal to the area under the M over EI diagram. So really the theorem is nothing but a single integration. So let's quickly take a look at a couple of examples. If we want to find, right, so I have this cantilever beam example up here and a simply supported beam example on the right. On the left, we know that if you apply a load P here, moment diagram would be like that, divide by EI, that would be your curvature diagram. And same thing for the simply supported beam, moment diagram, it looks like that. Now, if you want to find the slope at the tip of the cantilever, then what should how can I find that? If I want to find the slope at the tip of this cantilever out here, what should I integrate and between what limits? Okay, so let's integrate just following that equation. Theta at L minus theta at 0 is equal to the area under the M over EI diagram from all the way from 0 to all the way to L. And that area is nothing but the area of this triangle, half times base, which is L, times height, which is PL over EI, which is simply PL square over 2 EI. And clearly for the cantilever, rotation at 0 is 0. So that means this term drops out, and essentially theta at L is equal to this value. Straightforward. How about if I want to find the slopes at the ends of a simply supported beam like this? How can I find that? That's right. So if you can see that the deflected shape would be like this. At the center, since everything is symmetric, the slope would be 0. And if you subtract theta L minus theta L over 2, that's what we want. So applying the first theorem again, theta L minus theta at L over 2 is equal to the area under the M over EI diagram between the limits L over 2 to L. And clearly that is equal to half times L over 2 times PL over 4 EI, which is PL square over 16 EI. And once again, theta at L over 2 is 0. So the theta at the ends is PL square over 16 EI. So nothing terribly complicated. I'm sure you've all seen this before. I think the second theorem is a little bit more interesting. So let me talk a little bit about that, and also point out a little bit of a difference from what you might have seen in a previous course or in the book by Hibbler. So theorem 2, I basically think of that theorem as an incremental tangent at some point C, which is equal to the distance to that point C times the change in angle. That's the way I like to think about it. And if you remember that, then you don't need to sort of learn or memorize this statement of the theorem actually. So let's see what this really means. All that this equation is saying is that for any beam structure, if you take the M over EI diagram, or if you take the deflected shape, then this deflected shape going from some point A to another point B in the beam, that deflected shape occurs because of these small changes in angle d theta. So if I look at some small segment dx in that from going from A to B, that dx segment has a small change of angle d theta associated with it. So maybe I'll show this with this beam. I have this beam. If you look at some segment here, then this segment and this segment, they are separated by a small dx length, and there is a small difference in the angles between them too. Right? So that d theta is that small change in angle that I'm referring to. Now, if you were to draw tangents from that point to a vertical line at another point C, that small distance can be simply evaluated by geometry by taking the distance from the point C to that element dx and multiplying that with theta. So that's exactly what this theorem 2 says, that d tangent, that small incremental tangent, is equal to xc times d theta. Okay. If you take that equation and just multiply and divide by dx, you can see that this d theta dx converts to curvature. I can replace that with m over ei. And after integrating that from points A to B, you can show that x times xc times m over ei diagram, this hopefully you can see is nothing but the first moment of the area under the m over ei diagram, right? How do we calculate area? Integral dA. How do we calculate the first moment of area? Integral x dA. How do we calculate the second moment of area? Integral x square dA, right? So that's exactly what's going on here. I have an integral x dA, and so integral x dA is nothing but the first moment of area. So I am writing that as the centroid distance to C of the area under the M over EI diagram between points A and B. And the notation is slightly different here as well, because I think this is slightly more general than the notation given in your books. The way I refer to this quantity is calling it tangent from A and B measured at C, which basically in Hibbeler, in your book, the notation that they use is T of A with respect to B, which is actually nothing but T measured, the tangent from A and B measured at A, which is a little more restrictive. You don't need to measure it at A, you can measure it at any point you want. Okay. So this second theorem is a little bit more interesting. Go ahead. Question? Say that again. C is an arbitrary point. You choose wherever you want it to be. So you have the full freedom to choose C wherever you want. If you choose C, let's say out here at 0, then the distance xc would change. And that's how this second theorem is able to adapt to, to different choices of C, which helps you to be able to find certain quantities more quickly, rather than if you are constrained to using point A as the reference. You can put your reference anywhere you want, wherever it makes more sense. Okay, Philip?
We usually want one of your points A or B to be like if it's 0, like support. Or...
I'm sorry, say that again.
So for your points A and B, you usually want to pick one that has a deflection of 0.
It's not necessary, but for different problems, you have to pick different points for A and B. Sometimes middle of the beam is a good point because the slope there is 0. Sometimes, as you said, pick a point where deflection is 0. But for different problems, you would have to pick the points in a slightly intelligent way to try to apply this theorem and find deflections. But no matter what, if you pick enough number of points, you are going to get the answer. You might take a long route to get to the answer to find the deflection at a certain point, but this method will work ultimately if you choose enough number of tangents to measure. And I'll give you a simple example here. Let's look at the same two examples: cantilever beam with tip load and simply supported beam with a load in the middle. So in this case, if I'm trying to find displacement at L, delta at L, right, this guy. So following the notation that I just told you about tangents from A to B measured at C, what particular value or what particular tangent would this be? So if you look at the tangent at 0, that goes straight out here up to there, right? The tangent at L is clearly that guy, and I want to measure them at this point also. So tangent here, and I want to find the intercept at L. So I would call that tangent from 0 to L measured at L. Make sense? And delta L is nothing but tangent from 0 to L measured at L, which is equal to the first moment of area under the M over EI diagram between 0 to L. The centroid of that triangle is where? 1/3 of the base, right? So that distance from this point to the point where I'm taking the tangent at L, that distance is 2/3 L. And clearly the moment of that area would be the distance XC, that's 2/3 L, times the area itself, which is half times base L times height, which is PL over EI. Cancel off the 2's, and what we get is PL cube over 3 EI. Something that hopefully you all have seen many, many times. Deflection of a cantilever at a tip load with PL cube over 3 EI, right? How about this guy? Deflection at the midpoint of a simply supported beam with a point load. What I want to measure is the distance from here to here. So that happens to be the same as the distance between this tangent and the tangent from the middle point M measured at L. So what should I call this? That's right. So it's T, the tangent between from points M and L measured at L, right? Tangent from point M is this, tangent from L is this, measured at L because that's the distance I want. And clearly that would be TML, L. So the area under the M over EI, or area under the curvature diagram, is half the triangle because I'm going from M to L. And the distance measured at L is nothing but 2 over 3 L over 2. That's the distance XC times the area, which is half, times base, which is L over 2, times height of that triangle, which is PL over 4 EI. And once again, canceling this 2, and the denominator is denominator would be 4 for 16 and 3, 48 EI. Make sense? Okay, so again, this is all stuff that you've seen before, but these methods at least provide you a cross check for the new methods that we'll be learning in this course. Any questions or doubts about any of this? So once again, moment area theorem 1 is nothing but single integration. Change in theta is area under the moment, area under the curvature diagram. Theorem 2 is this incremental tangent is equal to XC times change in theta. And if you follow those steps, you can show that it gives you this well-known formula. Okay. And once again, I'll emphasize very, very much that rather than trying to memorize these formulas, try to understand where they come from, and it'll make applying those formulas much easier. Okay. All right. So I won't go through the conjugate beam stuff. Let's actually start this new chapter, which is hopefully stuff that that is maybe you've seen in physics or statics or somewhere else, but these will constitute new material for this course. Okay. All right. So what the main purpose of this segment of this course or this chapter is to try to find deflections of structures using energy methods. And there are two methods really that we'll see here. One is the principle of or real work and real energy, and another is a principle of virtual work and virtual internal energy. So essentially, this concept relies on the fact that that energy in a conservative system is conserved. If I have a closed system and if it's a conservative system, I'll come to what is a conservative system in a bit. But for linear elastic structures, these are conservative structures. They don't dissipate energy. So for example, I have this beam here, simply supported. I apply moments at the two ends. It deflects. And as it deflects, it stores energy within itself, right? So starting from a zero deflection, I slowly apply moments to it. And after I reach my some specified moment m, the deflected shape looks like this. If I remove that moment slowly, it comes back to its original shape, giving all the energy that it had stored back to me. Okay, and essentially that's what this concept of conservation of energy says, that the external work done on a structure is equal to the internal energy stored by that system. Can anybody give me an example of a system where this is not true? Say again. In viscous materials, there are two types of viscous materials, elastic and inelastic. So if there is inelastic viscous material, then you are going to dissipate energy. Okay, anytime you dissipate energy, then of course this is not going to hold true, right? Another example is doing work against friction. Whatever work you do against friction is lost. You can't really recover that. Okay. All right. So another simple way to see this is through this cartoon here. Let's say I have this spring mass system. Okay. The black configuration shows the original undeformed configuration of this spring. And I'm going to apply this load P to it very slowly. And after some point when I reach the full load, I get this deflection delta here. Okay. And if I were to try to plot the amount of load I apply with the deflection, then I can plot that on an XY plot that looks like this. Right? On the x-axis, I have the deflection. On the y-axis is the force that I'm applying. Mind you that I'm not applying that entire force P all at once. Let me ask you this: what would happen if I apply all the entire force to a spring mass system all at once? Yes. What would happen if I apply the entire force to the spring mass system all at once? Say it again. Yeah, it would oscillate. Like if you suspend a mass from a rubber string or a spring and just let it go suddenly, then you are applying the force at an instant. And indeed, in that case, you would get oscillations, something like that. And after some time, it would come to rest. Right? But if I apply that force slowly, my force goes slowly and my displacements grow slowly. So the amount of external work I do during that force as it grows slowly is just the area under the F times the force times displacement diagram. Make sense? Work done is equal to force times distance. So if I take that small change in distance dx, okay, I also take the force needed or through that displacement, then F dx is the integral that we would need to find the total external work. So it's F at x dx, and to find the total work done, I would need to integrate it between 0 to delta. Can somebody tell me what that expression would be for external work done on this spring going from 0 displacement to delta in terms of P and delta and all that? What would integral of this curve b from 0 to delta
Just be p times delta.
times half, right? It would be half times p times delta. It's the area of the triangle, nothing else, right? It's just half p delta. So for a linear spring, when the force is related linearly to displacement, I get a straight line in this external in this relationship of external force with respect to displacement. So for linear systems, it's always half times p times delta. External work done is half times the force times the displacement. Okay. How about the internal energy stored? When I have a displacement of delta in the spring and the spring constant is k, what's the internal energy stored in terms of delta? That's right, half k delta square. Indeed, you just substitute for p. P is equal to k times delta. So we have half times k times delta square. And for a linear system, it's just that simple. External work done on that system is stored as internal energy. When I remove that force, it expands back and returns that work to me, okay? Or returns that energy to me. Let's try to apply it to something that is non-trivial. Let's consider this truss, okay? So in this truss, it's a pin connection here and a roller support here. And at these bottom 2 points, I have these 2 loads, P1 and P2. They may be equal, they may not be equal. Okay. Now the way I'm loading it can differ in many different ways, but let me first start by just slowly increasing P1 and P2 simultaneously till they reach their final displacements of delta 1 and delta 2. Okay. I'm saying that I have this truss and I'll slowly load it, both of them at the same time, and reach the final point delta 1 and delta 2. If I were to plot that external force versus displacement, it would be a linear plot. It's a linear elastic truss. Make sense? Okay. So in this case, the external work done would be P1 times delta 1 integrated from 0 to delta 1 and P2 times delta 2 integrated from 0 to delta 2. Now let me when I do this external work on this truss, it deforms to that dashed truss that hopefully you're able to see. And in that configuration, the truss stores some internal energy. Thinking of that entire truss as some sort of a spring, it has deformed and it has stored internal energy, right? Now let me ask you a question. So if I load it differently, in the first step, I'm going to apply load P1 only. So I'm going to draw an alternate path here. In the first step, I'm going to load P1 and P2 remains constant at 0. And in a second step, P1 remains constant and P2 goes up to its full delta 2, right? So the end configuration, at the end of the loading, I still have the same P1 and P2 at those 2 points. Do you think the displaced shape or the deformed shape of the truss would be the same or different? How many say same? How many say different? So for linear elastic structures, indeed it would be the same, because no matter how you load it, the end configuration the end configuration will be the same, and it will store the same amount of energy, which is interesting because actually doesn't matter in which way you load it. You could follow some weird path to this loading for P1, another weird path for P2, and as long as the final load P1 and P2 is the same, you're going to end up with the same deformed configuration. And the internal energy stored in this truss, in this deformed configuration, is going to be exactly the same UI as if you were to apply those P1 and P2 slowly. Okay. And this concept really is what defines a conservative system. This concept that no matter what loading path I take, the final configuration and the initial configuration are the only things that decide the amount of energy stored in the system and what the deformed shape of that system is. So that is another way of saying that the system is path independent. And anytime the system is path independent, meaning I have two endpoints, no matter what path you go and take between those two endpoints, the state of the system at those two endpoints depends only on those two endpoints, not on the path you take to get there. And if you have such a system, then that system is conservative. Okay. So let me comment a little bit about what all of these other plots I have here. So as you're loading the system, as you're loading the structure with P1 and P2, each one of those members is going to deform. Some members are going to be in tension, and some members are going to be in compression, right? But each one of those members essentially acts like a spring. You can compress it or extend it, each one of those members. And that's what, so for example, I'm drawing this top chord AB. As I load from 0 to P1 and 0 to P2, the response of this segment follows along this line. This is the line that tells me that how stiff this member is. This is the internal force in that member and the displacement of that member. Let me ask you this again. Say I pick some weird path like this purple path I've drawn here. Would that translate to some weird path here, or would I always be along this line? This plot is nothing but the response of this member, response of, say, this spring. So when the spring is under zero force, I have zero displacement in the spring. When spring is under some specified force, that would be the displacement in that spring. So indeed, if I follow some weird path, it's not going to stray from this plot. It might go up and down this material response a couple of times, but ultimately it will end up at the point where this member reaches its final length. Okay, so that's what this principle of conservation of energy tells us. It says, as I apply these loads P1 and P2, doesn't matter what order I choose to apply these loads, in what order I apply them, the internal energy stored in the truss will depend only on the final configuration of the truss, and that final configuration essentially depends upon what the lengths of all of these members are. So if you draw the change in lengths versus the internal forces in them, you can figure out what would be the internal energy stored in that truss. And very quickly I'll write that, and I think we'll be done for the day. So internal energy stored in a system, in a spring system like this, as you can see, we calculated that to be half k delta square, or another way to write that is half times n1 times delta 1. So basically I can write that as half times nm times delta m, and sum that over m going from 1 to capital M. What that means is if there are capital M members in this truss, then half times the internal force times delta. That's the energy stored in each one of those members, right? That's what we calculated up here. For a spring like this, the energy stored, which is equal to the external work done, is half times P times delta. And if I sum that up over the entire structure, then that gives me an expression for delta M. And using the fact that all this external work is equal to the sum of all the internal works, I can find the displacements, and that we'll look at next time. So let's stop here, and on Friday, Dr. Liu will revise some of these things, and we'll do some in-class activities on Friday. And once again, please do complete that survey, and you'll get an extra bonus point for doing so. So see you all on Friday.